In this video, we're going to take a look at how to compute volumes of solids of revolution using the disk method when the axis of rotation is the y-axis. So when the axis of rotation is the x-axis, we know that the cross-sectional area is going to be pi times the radius of our disk at x squared, and therefore the volume, which in general will be the definite integral from a to b of our area, cross-sectional area function, in this case will be the integral from a to b of pi times our radius squared dx. However, when the axis of rotation is the y-axis, we have to think of things a little bit differently. In particular, we need to consider everything as functions of y instead of as functions of x. In particular, that means each of our curves has to be thought of as x equals a function of y, say x equals g of y, instead of how we typically think of functions as y equal f of x. We also need to think of the region being bounded between two particular y values. Instead of being between x equal a and x equal b, we're going to bound our region or our solid between y equals c and y equal d. The formula for our volume is then very similar to when we're rotating around the x-axis. The volume is given by the definite integral from y equals c to y equal d, so the lower and upper bounds along the x-axis for our solid, and we're integrating the cross-sectional area of our curve, which is pi times the radius squared, and here the radius is given by a function of y, capital R of y. Of course, we also want to integrate this function or this integral in terms of y, so we do want a dy here instead of a dx. In this example, we want to find the volume of the solid obtained by rotating the region bounded by y equal x cubed, y equal 8, and x equals 0 about the y-axis. Our first step here is to sketch the region and solid that we're being asked to consider. And so to do that, the first thing that we need to do is sketch the curves that bound our region. The first curve that we're given is y equal x cubed, and that looks something like this. So this will be y equal x cubed. We also have y equal 8, which is a horizontal line that intersects the y-axis at 8, so somewhere up above the x-axis there. And x equals 0 is the y-axis, and so we have this curve here. And so we want the region that is bounded by all three of these curves, which is this region right here that is now shaded in blue. Now we want to rotate this region around the y-axis. And when we do that, the other side over here will be sort of a mirror image of what we have. And so our solid will consist of this region over here. And because of the rotation, we'll see the cross sections there since we're rotating around the y-axis, which is part of the border of our region. We're going to get disks, cross-sectional disks, all the way through here. By looking at our solid, we can easily see that the solid sits between the value c equals 0 on the bottom and d equal 8 on the top. And these are the values along the y-axis that bound our solid. And so our integral that we're going to use to compute our volume is going to be the integral from 0 to 8. The last thing that we need is we need to find the radius of a cross-sectional disk at some value of y. And here, that radius will be given by the distance from the y-axis to the curve y equal x squared. In order to find that distance, we need to think about that curve as being a function of y and not as a function of x. Now here, this is pretty easy to do. Y equal x cubed can be converted to a function of y by just taking the 1/3 power of both sides. And so here we see that curve can also be written as x equals y to the 1/3, or the cubed root of y if you'd prefer writing it in that notation. So here we have some value of y where we're taking this radius, and so what we see here is that our radius function, r of y, will simply be y to the 1/3 or the cubed root of y. We now have all the necessary ingredients to compute the volume of this solid. We know that we're going to be using the disk method, we know the radius of each of the cross-sectional disks, and we know the y values where the disks will be taken, in particular from 0 up to 8. And so now we use our integral formula and compute the volume. So the volume will be given by the definite integral from 0 to 8 of our cross-sectional area, which is pi times our radius squared, and our radius is y to the 1/3. So we have y to the 1/3 quantity squared dy. And of course, this simplifies to the integral from 0 to 8 of pi y to the 2/3 dy. So we find an antiderivative using the power rule. So an antiderivative of y to the 2/3 will be y to the 5/3 multiplied by 3/5. And then we want to evaluate that from 0 to 8. So we can clean up these constants out front and get 3 pi over 5. And we want to compute 8 to the 5/3 minus 0 to the 5/3. Now, of course, 0 to the 5/3 will simply be 0. For 8 to the 5/3, we can actually simplify this a little bit. We can think of this as 8 to the 1/3 power raised to the 5th power. And 8 to the 1/3 is the cubed root of 8. And so that's just 2 to the 5th power, which we know is 32. And so this particular volume we can think of as 3 pi over 5 times 32. And that will be 96 pi over 5. And so this will be our exact value for the volume of the solid that we obtained here in this example. If you'd like to try a similar example, pause the video and find the volume of the solid obtained by rotating the region bounded by y equal 4 minus x squared, x equals 0, and y equals 0 about the y-axis. For your convenience, the sketch of the region is shown here below. Resume the video in a few seconds to see the worked out solution. When we form our solid by rotating our region around the y-axis, we can see that the solid is going to lie between the values of y equals 0 on the bottom and y equals 4 on the top, which means c is 0 and d is 4 in our integral formula for the volume. If we look at a random cross-section somewhere in the middle, we do get a disk since our region borders the y-axis, and we need to find the radius of that disk at a particular value of y. In order to do this, we need to convert y equals 4 minus x squared to be a function of y, so we can simply just solve that equation for x. And we can do that by first writing x squared as 4 minus y, and then taking the square root of both sides and getting x equals the square root of 4 minus y. Since we're in the positive x value range, we're going to take the positive square root here. And therefore, the radius of our cross-sectional disk at any given y is going to be the square root of 4 minus y. We now have all the ingredients for our definite integral to compute the volume, and so we substitute all of our values in and actually compute the volume. Squaring the radius gives us an integrand of pi times 4 minus y. We find an antiderivative of that, pi times 4y minus y squared over 2. Evaluate that from 4 to 0, and that results in the volume of 8 pi.